Hi, this time we're talking about projectile motion, and specifically we're talking about horizontal projectiles. So the question I'm asking first is, how would one describe the path of a projectile? For say I have a cannon on a cliff here, how would I describe the path of this cannon? Now, hopefully we've watched enough pirate movies or old colonial time movies where we've seen cannons being launched in the air and we see what happens. Well, we can see that a cannon doesn't follow a diagonal. That's not what it does. A cannonball follows an arc as it flies through the air. And we're going to dive into why it follows an arc. Like, what's the purpose of that? What's the reason of that? So here we are. There's my arc. Let's first talk about X and Y here. In math, you're used to not being able to just add X's and Y's because they are not simply addable. Well, in this case, with a projectile, your X motion and your Y motion are not something you can just add together. Instead, one of the big themes of this chapter is that horizontal and vertical motion are independent of one another. I cannot stress enough how important that idea is, that the X and Y motion are independent. So let's focus just on X motion for a minute. And let's imagine that our cannon has an initial velocity represented by this red arrow. Let's go and just say it's 100 meters per second for fun. So our cannon has an initial velocity of 100 meters per second. When you think about things that could affect the flight of this cannonball, and some people say, well, air resistance, and that's fair. Air resistance would certainly slow down the cannonball. People say gravity. Okay, gravity is certainly going to act on the cannonball, but gravity is up and down. Gravity is not horizontal, so think about more horizontal things. And when you keep thinking, you won't be able to come up with anything. Now, if you tell me, well, the cannon pushes on it. Well, once the cannonball leaves the cannon, there's no more pushing. It's done. Its job is over. So there's really nothing if you ignore air resistance. There's nothing to affect the horizontal flight of the cannon. So, no. So what happens is, because there's nothing to affect the horizontal flight of the cannonball, that makes this really cool thing happen. Your velocity in the X direction is, I'm drawing with the mouse. I apologize for my writing. Constant. The X velocity is constant. That means if our cannonball starts out traveling 100 meters per second in the beginning, that means after time 1 it's 100. After time 1 it's 100 meters per second, 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 and so forth. It's just going to keep going 100 meters every second. So that's a really cool thing about our projectiles. Then let's talk about vertical. Vertical motion. Is there anything to affect the flight vertically of a cannonball? Well, yeah, gravity. Gravity certainly is going to act on it. Now, in the beginning, when the cannonball is still in the cannon, is it falling yet? Well, no, not yet. But as soon as it leaves the cannon, it begins to fall. Now, in the beginning, that vector is very small. It's not had much time to accelerate downward. But you can see how, as time proceeds, the cannonball gets to accelerate downward and go faster and faster and farther each second downwards because it's accelerating. Okay. Now let's take a peek at equations. And I don't want to dwell on these equations over here, but I just wanted to show you how these equations came from the old ones for a sec. Focus on this one right here. This is one of our favorites. Delta y is our height. How far will my cannonball have gone in a certain time? Okay. In a certain amount of time, how far will my cannonball go? Or, I am so far above the ground, it will take this long to reach the ground. And these are nice, but we don't usually look for the final velocities in the vertical of our cannonball that often. But this here, how far does our cannonball go? That's a big deal right here. Our delta x. Now what's cool is, because velocity is constant, it's just displacement equals velocity times time. So the biggest thing, the glue that holds together projectiles, is this time right here. That is the same time in both equations. Same exact time in both equations. And that's a big deal. Want to do a little sample? Let's do a little sample. I got a sample here. Reset. We use this in the bell work today in class, and Bob goes jumping off the ship. Now I tell you that Bob's 10 meters above the water, or above the deck of the other ship, and he runs sideways at 10 meters per second. Will he go 23 meters? So we don't want to use 23 meters in that calculation. We want to calculate how far he will go and check it with 23 meters. So to do this, we need a couple equations. Let me sneak back here and steal this equation right here. Copy. So Bob is 10 meters above the deck. So right there, 10 meters. 10 meters equals half a g times t squared. Now, you guys are able to do some math. If you take that 10 meters, and you know what? In all likelihood, we probably should make that negative. Because most likely, you're going to write that g as a negative. And we want to have our signs agree. So if you take that 10 meters and you divide by half a g, you're going to get like 2.04 or something very close to that. And then when you square root it, you'll find that the time of fall is 1.43 seconds. So it takes Bob 1.43 seconds to reach the height of the ship's deck. Well, then we look and say, okay, Bob's traveling 10 meters per second. Let's go steal another equation. Go steal this equation now. Please? I just want that part. Back over here. Paste it. What went over there? You silly. And so now we take our 1.43. Right, I don't want to move the whole boat. I'll just rewrite it. We take our 1.43 seconds, and we want to multiply this by the 10 meters per second that Bob is running. Meters per second. And if you take 10 times 1.43, you end up with 14.3 meters. Well, gosh, if this is 23 meters, 14.3 is, well, maybe there? Bob does not make it. He falls right here. Now, the big focus right now should really not be Bob's fate. The big focus really should be this tandem of equations. When you're doing projectiles, these two are your favorite. And most of the time, it seems like you're given your delta y. You're given the height to use. And when you're given the height, you should find a time with that. Now, whether you're finding the velocity or you're finding the displacement, that's an either or, but you'll be given the either or that one or the other. Okay? So this is horizontal projectiles. Just remember that the x and y axis work independently, and they're affected by different things. The x-axis is affected by nothing. It's just constant, and the y-axis is affected by gravity.